China has built its first domestic prototype of an EUV lithography machine. The national effort pulled together so many resources that many compare it to China's Manhattan Project. But one detail stood out immediately. The prototype reportedly occupies an entire factory floor. Why is it so much bigger than ASML's machine? And more importantly, how did China rebuild it without access to its most critical parts? I started researching this expecting a story about reverse engineering. But what I found is way more interesting. As a semiconductor engineer, what surprised me most wasn't what China copied, it was what it chose to do differently. So in this video we will take this new Chinese EUV machine apart piece by piece, to see which parts China rebuilt, which ones it approached differently, and where it still hasn't caught up. China's first challenge was build the one thing every EUV machine depends on – the light source. Every EUV lithography machine is essentially a giant printer. Except instead of spraying ink onto paper, it prints microscopic circuits onto silicon wafers. And the smaller those circuits become, the shorter the wavelength of light you need. That's why today's most advanced chips rely on 13.5nm extreme ultraviolet light, so-called EUV light. There is just one problem. You can't buy a 13.5nm laser, you have to build one. ASML's solution is remarkably elegant. Every second the machine fires 50,000 microscopic tin droplets into a vacuum. A small laser flattens each droplet into a tiny disc. Right after, a far more powerful CO2 laser hits exactly the same droplet. The tin instantly turns into plasma, reaching temperatures of around 200,000 degrees Celsius. As it cools, it emits 13.5nm EUV light. But in practice, it means hitting 50,000 microscopic moving targets every second without missing a single shot. After decades of development, ASML finally made it work. And for almost 20 years, that became the blueprint for every EUV machine. And that is a machine China suddenly had to build itself. So they faced a choice. Rebuild ASML's approach or find a different path to the same destination. Publicly available reports suggest that China is trying both. One became the foundation of every ASML machine, the other is called laser-induced discharge plasma, or LDP. Instead of chasing 50,000 flying tin droplets every second, LDP starts with two metal discs rotating slowly. Each disc sits in a bath of heated liquid tin. As the discs spin, they get coating of tin on their surface. These discs are electrodes connected to massive banks of capacitors sitting there fully charged. A small laser fires at one disc. That's the trigger. The laser vaporizes a tiny amount of tin, creating a cloud of tin vapor that hangs between the two discs. Now the capacitor dumps their stored energy, and a huge electrical current jumps straight through that cloud. The current generates a magnetic field, crushing the vapor into plasma that's incredibly hot and dense. We are talking hundreds of thousands of degrees. And that plasma emits 13.5nm EUV light. Same light, but radically different engineering with some compelling advantages. No giant CO2 laser, no need to hit 50,000 moving droplets every second, which means way higher chances to hit the target. So it's potentially way more efficient and mechanically simpler machine. So why didn't ASML build the EUV machine this way? Well, 20 years ago they actually tried. The challenge wasn't creating EUV light, it was creating enough of it. Factories need hundreds of watts of stable EUV power, because without it, every wafer takes too long to expose. Just imagine trying to cook dinner with the heat from a light bulb. You might get there eventually, but no factory can afford to wait that long. So, historically, LDP approach hits a physics wall. As engineers bumped more energy into the plasma, it grew larger, but not brighter. And the mirrors simply can't collect the most of it. So you keep adding power without getting more usable UV light. And eventually, ASML just moved on, not because LDP approach was impossible, but because 20 years ago it couldn't be scaled to manufacturing. As a result, this approach topped out at 30 watts of output power, while latest ASML LPP-based prototypes now reaches over 700 watts. So ASML switched and never looked back, because this approach was impractical, at least at that time. And this is a very important distinction. China isn't betting that LDP was smarter than the approach ASML chose. It's basically betting that 2026 isn't 2006. And latest reports suggest that China has demonstrated both conventional LPP prototypes and continues to actively develop LDP. However, the output power and yields are still well below what is needed for high-volume manufacturing. But for the first time, China has built its own EV light source. At this point, it almost feels like they've solved the biggest challenge. But surprisingly, the light was just the beginning. Because now you have to focus that precious light onto a silicon wafer. And here is a problem. Glasses, cameras, microscopes, they all rely on lenses, and EUV machine can't. At 13.5 nanometers, almost every material simply absorbs the light. Glass doesn't bend it, it swallows it. So engineers had to rethink the entire optical system. So instead of lenses, they use a chain of mirrors that bounces the light all the way to the wafer. But these aren't ordinary mirrors. Each mirror is built from dozens of atomically thin layers of molybdenum and silicon. Light has to go through many stages of mirrors, and every reflection loses at least 30% of it. By the time the beam reaches the wafer, only a tiny fraction of the original light remains, and that leaves almost no room for error. And every mirror has to be atomically smooth. Building them is extraordinarily hard, but measuring and aligning them is even harder. For decades, there was only one place on Earth that knew how to build mirrors like this: Zeiss. Not because of one particular invention, because they spent decades perfecting every single step. Polishing, coating, measuring and aligning mirrors with atomic precision. That's the difference between building a mirror and building an EUV mirror. So how did China recreate 3 decades of optical know-how without Zeiss? And why does its prototype reportedly occupy an entire factory floor? The answers are much more interesting than I expected. But first, these days getting the best results from AI usually means using multiple models. Gemini for research, Claude for coding, Nano for images, Kling and Runway for video. It quickly turns into too many tabs and too many subscriptions, and it keeps growing. That's where Chat LLM from Abacus AI comes in. One dashboard gives you access to the top AI models, and Root LLM automatically routes tasks to the best one. If you need fast responses or serious coding help, Root LLM picks the best model for the task, like Claude Opus 4 for coding or Gemini 2.5 Pro for reasoning, and they add every new model within minutes of launch. You can also create professional presentations with charts, graphs, deep research and detailed content in minutes. And if you need your writing sound more natural, their humanized tool rewrites AI-generated text into smoother, more authentic language. Choose from frontier and open-source image models like Nano, Midjourney and Flux. You also get Magnific for upscaling, plus Kling, Cdance and Runway for AI video generation, all built in. And there is more. It also includes Abacus AI Agent, which can build apps, websites and entire workflows from a simple prompt. And the best part, it starts just at $10 a month, which is less than most people pay for a single premium AI subscription. Check out Chat LLM by Abacus through the link below to streamline your entire AI workflow. Generating UV light was only the beginning. Now China faced the problem that took Zeiss more than 30 years to solve. But how do you recreate all that experience? China broke the problem into smaller pieces. One of the most important was the Changchun Optics Institute. It focused on precision optics and optical alignment, because building an EUV mirror is unlike building almost any other optical component. The surface has to be smooth to around 50 picometers, less than the width of an atom. Actually, China already builds world-class optics for space telescopes. But EUV mirrors is an entirely different story. This level of polish on a curved surface is Zeiss' secret sauce, built over more than 30 years. And even verifying those mirrors requires measurement tools that barely exist outside ZEISS. But that's only the beginning. Because inside an UV scanner, the mirrors are constantly bombarded by hot tin plasma debris and intense UV radiation. Keeping those coatings stable for years inside a productive machine is another challenge entirely. Public reports suggest that Chinese institutes have already demonstrated domestic UV mirrors and integrated them into prototype optical systems. Matching ZEISS, however, is a very different challenge, not just in optical quality, but in reflectivity and durability after decades of production. So China appears to be making a different engineering trade-off. If your mirrors are less efficient and your light source is dimmer, one way to compensate it is with scale. Larger collectors and lasers, longer optical path, and bigger mirrors. It's the engineering equivalent of saying, if you can't make it precise, make it just bigger. That may help explain why China's prototype occupies an entire factory floor, while an ASML scanner is roughly the size of a school bus. Reports suggest that Changchun Optics Institute have now integrated domestic optical systems into China's prototype scanner. That doesn't mean China matched ZEISS quality. Far from it. Overall, optical performance also appeared to remain way below commercial UV scanners. But that's still a significant milestone. Because for the first time, China appears to have assembled a domestically developed optical system capable of operating inside an UV scanner. And that brings us to the next bottleneck, something you can't polish away or engineer, because it's one of the lightest elements in the universe. It's helium. The same gas that fills party balloons, and yet one of the most important machines humanity has ever built can't run without it, because its physics are almost impossible to replicate. Helium is essential in EUV tools as well as in chip manufacturing, because there's nothing else that can do all of its jobs at once. It carries heat away from some of the hottest parts of the process. It doesn't react with delicate optics or silicon wafers. And its atoms are so small that it's used to find leaks too tiny for any other gas to detect. Replace helium, and chip production stops with it. And EV machines don't just use some helium, they drink huge amounts of it. A single advanced fab can require 5,000 to 20,000 cubic meters every month. And there is no practical substitute, which creates a new problem for China. It imports roughly 85% of its helium. Domestic production is under 900 tons a year. Import exceeds 4,900 tons. And historically, most of that supply came from just two countries, Qatar and Russia. Then both supply chains came under pressure. The problem is, unlike oil, helium can't sit in storage forever. It's transported as a cryogenic liquid, and it's very time-sensitive. If shipping is delayed long enough, it slowly boils away. Once it escapes into the atmosphere, it's gone. Meanwhile, the world's largest helium reserves sit somewhere else, in the United States and in Qatar. This isn't just China's problem, it's everyone's problem. It's a problem for TSMC, Samsung, Intel, and SK Hynix. Basically, every advanced semiconductor manufacturer draws from the same supply chain. And now China is trying to build an entirely domestic EUV ecosystem while depending on a material it largely doesn't control. That's why Beijing reportedly imposed an emergency ban on all helium exports, because they're hoarding every molecule they have for chip factories. And the deeper I got into the story, the more I realized that EUV scanner isn't limited by one invention. It's limited by thousands of invisible dependencies. Some are billion-dollar mirrors, some are decades of optical know-how, and some are just a colorless gas almost nobody thinks about. Even if you solved the light, built the mirrors, and secured the helium, one challenge still remained: the people who knew how to make it all work together. Because there is one thing sanctions could never stop: knowledge. You can block machines and components, but you can't block what's already inside someone's head. And that may have been the greatest ASML advantage all along. So China didn't just invest in labs. and research institutes. It invested in experience. Some of the best talent working overseas were recruited to return and joined one of China's highest priority technology programs. One of the best known examples is Li Nan. He spent years at ASML working on the EUV light source, arguably the most challenging subsystem in the entire machine. After returning to China, he joined the Shanghai Institute for Optics and Fine Mechanics, where his team rapidly began publishing research and filing patents related to EUV light generation. And China is investing so much money and putting so many smart people into that project that effort is starting to show. When you look at research publications on EUV lithography, a clear pattern emerged. For years, China published relatively little. Then, around 2020, the research suddenly takes off because dozens of teams started attacking different parts of the problem in parallel. So, where does that leave us? Reports suggest that China has now a working EUV prototype, and it currently delivers around 100 watts. While ASML's production systems deliver roughly 300 watts, with some of the newest prototypes reaching 700 watts. And that's still a substantial gap. But does China need to match ASML? I don't think so. Today, SMIC manufactures its most advanced chips using quadruple pattern DUV, deep ultraviolet lithography, which is an older generation of lithography machine. In this process, the same wafer has to pass through the lithography machine 4 different times. It works, but the yields fall below 50%. Time and costs rise dramatically, and eventually the physics stops you, because you can't keep shrinking transistors like that forever. You won't get with that to a 5nm class equivalent process node. This means a domestic EUV machine doesn't have to become the world's best. It only has to become better than the alternative. Even if it prints fewer wafers, even if it's not commercially competitive, even if yields are far below ASML's. If it can only replace quadruple pattern DUV, it already will be a huge win for China's semiconductor industry. And remember, ASML needed roughly 12 years to go from its first EUV prototype to a commercial product. China will almost certainly need time as well. But unlike ASML, this isn't just a commercial project, it is a strategic one. The objective isn't necessarily to build the world's best EUV machine, it's to build one China controls. And then comes the part no one can shortcut, turning a working prototype into a factory. Because the distance from it worked once, and it runs 24 hours a day printing hundreds of wafers every hour for years, is enormous. If you enjoyed this episode, make sure to share it with your friends, and now watch this one on Chinese logic folding or this one on IBM's new 0.7nm transistor breakthrough. I'm sure you will enjoy both. Love you guys, and I'm gonna see you in the next one. Ciao!